gonna talk about sequences which start on page 505. So if you take a look at page 505, there's basically this little drawing or little diagram at the top of the page, and it talks about how like somebody's building a house of cards or building a tower using playing cards. So hopefully you can kind of like imagine this scenario while you are thinking about this little diagram. So row 1, row 2, row 3. And so you can imagine if you were to build a house of cards like that, you could, I mean, it's kind of weird because you can't really build by increasing the rows on the bottom. Obviously, you would have to like set up the bottom row first and then move to the higher row and move to the higher row and move to the higher row. But let's just imagine that we could continue this onwards. So let's just take a little bit of space here maybe. And if we imagine, so my first row, it's basically, it has to have 3 cards, right? 1, 2, 3. Because there's going to be that card that kind of acts like the floor. Here, let me just, so 1, 2, 3. So that's how we get over here for row number 1, there's 3 cards, right? So for row number 2, if I'm going to try to add to this, I would need to be like 1, 2, 3, 4, 5, 6. So see how I would add 6 cards, which is why that's a 6. So how many cards did I have to add for row 3? Well, let's think about that. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So I had to add 9 cards. Okay. For a 4th row, I'm going to have to add 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 cards. For a 5th row, I'm going to have to add, kind of running out of space, but that's fine. For a 5th row, I'm going to have to add 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And you could imagine if you're trying to build a really, really big house of cards, then it would continue on like that for a long time. So let's just take that for what it is for right now. Let's talk about number of triangles in the row. So number of triangles in the row, of course, 1, then we have 3 triangles, 1, 2, 3, then we have 1, 2, 3, 4, 5 triangles. In the 3rd row, again, always thinking that the top row is row 1, then the next row, row 2, next row, row 3. Row 4, how many triangles do I have? 1, 2, 3, 4, 5, 6, 7. Row 5, how many triangles do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9. Okay, so why are we talking about this? What's going on? So the thing to notice is that both of these tables give us a sequence, which is basically a list. So we have a list of numbers, right? And notice how if, let's say we have sequence A, we'll take that from table A. If that is 3, 6, 9, 12, 15, you can basically start to see that, like, or if you think about it this way, you can see that it's going up by the same amount. See how every time I'm basically adding 3. I'm adding 3 to get to the next number in the list. Again, I'm adding 3. Again, I'm adding 3 to get to the next number in the list. And this is called an arithmetic sequence. Arithmetic sequence. So at the end of the day, it's pretty much a list of numbers. And the main kind of defining characteristic for the arithmetic sequence is that it's increasing or decreasing the same amount, like to get to the next term in the list. A list of numbers. Each subsequent number increases / decreases by the same amount. We can see here this arithmetic sequence, it is increasing by 2. So you could start to think about how each of these could actually continue on indefinitely. Like, if basically all I need to know is that for each subsequent row number, let's say row 6, row 7, row 8, something like that, I can basically predict without drawing anything. I can pretty much just think about the way that this sequence is changing each time and basically just go from there. So let's say I wanted to figure out, well, what's my 6th row? Well, I know it increases by 3, right? That's what I saw. For that sequence A, table A, it's increasing by 3. So that tells me, oh, well, row 6, it has to have 18 new cards added. Row 7 has to have 21 new cards added. Row 8 has to have 24 new cards added. Down here, we're increasing by 2 every time, so I know that there's going to be 11 triangles in the next row. I know there's going to be 13 triangles in the next row. I know there's going to be 15 triangles in the next row. So that's that's literally how that works. So we will keep going through examples, and we'll get more general about how we can talk about this, but that's basically what an arithmetic sequence is. So yeah, that's the fundamental idea. We will kind of generalize that a little bit with like a formula. But at the end of the day, that's what's happening. So yeah, why don't I just draw this in here just for the sake of clarity. All right, so cool. Let's move on to a next example, because I think it's kind of everything that needs to be said about that example. Okay, so this is called Pascal's triangle. And basically the way that Pascal's triangle works, I'll probably just draw it myself to kind of explain a little better and take a little bit more space to do that. So, okay, so Pascal's triangle, basically the way this works, if we take a look over here, we have the top two rows, 1, 1, 1. Okay, so what's even going on there? So what's happening is 1, 1, 1, and then imagine that we kind of like extend down, and we're always going to add a 1 on like the diagonal of that triangle. So we put the 1 here, we put the 1 here. But then where these other numbers come from is like, well, what's the sum of these two numbers? So what's the sum of these two numbers? Well, 1 plus 1 is 2, right? So that's how that works. So to extend the triangle again, we're going to say, what's the sum of these two numbers? Well, the sum of those two numbers, 1 plus 2 is 3. 2 plus 1 is 3. And then we always extend on the diagonal with the 1. So we could keep doing this for forever, basically, if we wanted to. Let's just do it for a couple rows so we get a sense of how it works. But 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And then we, again, continue with the 1 on the diagonal. So, and you can see each subsequent row has one additional number in it. There's 1 number here, 2 numbers here, 3 numbers here, 4 numbers here, 5 numbers here. The next row will have 6 numbers. What will those numbers be? Well, let's see. We're always going to be summing these two numbers to find out what the numbers in our next row is. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And then again with the ones on the diagonal. So just, yeah, there's always going to be those ones along the diagonals. That's not the best way of drawing that, but let's try this maybe. I'm just pointing out that there's always going to be those ones on the diagonal. Okay, so what are we even talking about here? We're talking about what is the sum in each row, and we can figure that out not too painlessly, I think. You can see, yeah, sum of 1, row 1, obviously 1. 1 plus 1 is 2. 1 plus 2 plus 1 is 4. This is going to be 1 plus 3 plus 3 plus 1. That's going to be 8. Let's talk about row 5. So row 1, row 2, row 3, row 4, row 5. So that's got to be, well, 14 plus 2 is 16. This is going to be 20 plus 30, 32. So here's the thing. Do I even really need to draw the next row to understand what might be the sum of the numbers in the 7th row? I mean, like, whatever, I technically could, but I can also notice that there's something going on here with this sequence, and hopefully I'm able to notice that these numbers are doubling. So you can see to get from 1 to 2, that's a times 2. To get from 2 to 4, that's a times 2. To get from 4 to 8, that's a times 2. To get from 8 to 16, that's a times 2. 16 to 32 times 2. So, I mean, I kind of have to expect that the next row would have 64 as the sum of the numbers. Why don't we just show that that is going to be the case? Just partially out of curiosity, I don't know, just wanting to maybe try it out. So just remembering I'm going to sum. You don't really have to, I mean, I'm just drawing these arrows so I kind of keep them all spaced out properly. So 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. 6. And then, of course, I always extend with my 1s on the diagonal. So that's going to be 20 plus 30 is 50. 62 when I add 12. 64. So that is definitely, that sums to 64. So we've already talked about we've already talked about arithmetic sequences. That's what we saw in the first example, which actually my computer got super frozen, and so I can't even like flip back to the image right now. If you see, like, I lost that or whatever, but arithmetic sequences were always increasing or decreasing by the same amount to get to the subsequent term in the sequence. But you can see here, something's not being added. It's not an increase or a decrease. It's not a linear increase or a decrease. It's not always going up by the same amount. It's always being multiplied by the same amount. So this would be a geometric sequence, which is kind of different, right? Arithmetic, we saw it was always plus 3, plus 3, plus 3, plus 3, plus 3 in the previous examples, or plus 2. But here, something's being, it's going up by like a multiplication factor, so that's a little different. And this is just a picture that I found of Pascal's triangle. And yeah, you can see it does continue on like that. And theoretically, it could continue on infinitely. Okay, so here's another example. Hopefully you can kind of get a sense of what's happening here. You can see we start with one triangle, and then to get to our subsequent term, we add another triangle inside the drawing. To get to that subsequent term from here to here, we add another triangle inside that drawing. So let me draw what diagram 4 and 5 must look like. Okay, so I'm going to try to draw diagram 4 and 5. So imagine, first, for the first diagram, I have this one triangle, so that would be diagram 1. Then diagram 2, I add in another, okay, fine. If it's not going to become a straight line, that's okay too. Well, actually, I can switch to lines here. So that's diagram 2. Diagram 3 is like that. Diagram 4, I would need to add in another little triangle. And see how it's getting kind of hard to do this, right? Because it's kind of getting like infinitely small if I were to keep going. Okay, right. So this would be diagram 4. Oh wait, yeah, that would be diagram 4. And I bet I can just copy and paste this somehow. There we go. So diagram 5, we would just need to add in that tiny little triangle. So, and it would be hard to draw diagram 6, right? Unless we started really big, just because that's getting really tiny. So let's see, what was it asking us about even? It was asking us about, okay, side length of the triangle. Okay, well, here's the thing. Let's say that original, we don't have to measure anything here. If this original side length of that original triangle is 32, this triangle has to be half as big, right? So it has to be 16 centimeters. No measuring is needed, but just the fact that if that triangle's half as big, it better have half the same side length, right? So then I know for my third triangle, that side length has to be 8, because that's half of 16. 4 is half of 8. 2 is half of 4. Number of triangles of any size. So this is getting a little weird, right? Because number of triangles of any size, sure. Diagram 1, there's only 1. But let's just figure out, wait, how are there 5 triangles here? Well, there's 1, 2, 3, 4, but then there's also the 5th. This is like the 5th triangle. So that's how we end up with 5. So with that in mind, how do I do this? So I have 1, 2, here, I'll count this way. 1, 2, 3, 4, 5, 6, 7. But then I also have to have 8 8th triangle. I definitely still have 9th triangle. So unless I'm missing something, I feel that must be it, right? Because I've counted 1, 2, 3, 4, 5, 6, 7, 8, 9. I think that must be it. It's just like, again, there's no answer key for this stuff. So 9, let's say there's 9 triangles there. Let's just double check down here. So here, let me count my regular little triangles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But then there's still 11, 12, 12, and 13. So 13 triangles. And you know, I'm starting to see a sequence, right? Something's going up by a predictable amount every time. It seems like maybe that next diagram would probably have 17 triangles in it. Okay, so finally, if the average daily temperature in Prince George on December 1st was 8 degrees Celsius, and for the next 6 days it's decreasing by 4 degrees each day, well, this is pretty chill. If the temperature is decreasing 4 Celsius each day, well, that must be 4. This must be 0. This must be -4. This must be -8. So here we are, it's still going to be an arithmetic sequence. Because remember, with arithmetic sequences, we were able to, or well, we had to, an arithmetic sequence always is going to be increasing or decreasing by the same amount. Here, we happen to be decreasing by 4 every single time. It's the same thing every single time. So that's how that would go.